In this presentation, we're going to cover some general aspects of waves. We're going to get a little less mathy in this one. There will be a little tiny bit of math at the end, but in general, it's going to be more conceptual. So, first things first, waves, you have to remember, are basically bundles of energy that travel from point A to point B. Sometimes they need something through which to travel, and sometimes they can travel through the emptiness of space. Waves that require some mechanical medium through which to travel are called mechanical waves. Waves like light are called electromagnetic waves. They can go through media. For example, we know that we can see the bottom of a pool, which means that light must be going into the water, bouncing off the bottom of the pool and coming back to our eyes. So we know that light can go through a medium, but light doesn't require a medium, as evidenced by the fact that sunlight comes to us through basically the emptiness of space. So we're going to talk about waves in general, and then we're going to talk about sound. Toward the end of the semester, we will talk about light, and we'll find out then that when we use the word light, we don't just necessarily mean visible light, the thing that our eyes can see. All other forms of electromagnetic radiation are considered light. For example, X-rays, gamma rays, ultraviolet rays, and so on. Those are all similar to visible light. It's just that we, coincidentally, can see that part of the electromagnetic spectrum. More on that later. In general, waves can move along in two different ways. One is as a transverse wave. The term trans means across. Okay, so this is going to be a traditional wave where, for example, you guys played with slinkies earlier. If you have a wave like this, and let's say that you've got the person on the left is generating these waves, and those waves are moving left to right. The slinky itself is not moving left to right, it's moving up and down the way I have it drawn here, okay? So that's what we mean by transverse. The wave actually moves perpendicularly to the direction that the medium is moving. In a longitudinal wave, like sound, so we may want to write this down or actually circle it down here, the medium actually moves back and forth along the same direction that these wave pulses travel. You notice that you've got higher density areas here. These are called compressions, and in between the compressions you have less dense areas called rarefactions. Now a wave in a slinky would be created, a wave like this in a slinky would be created by rapidly shoving the slinky in one direction, creating this compression, and then as the compression starts moving along the slinky, you would rapidly pull the slinky backward, creating this less dense area like this. And you do it alternatingly to create these alternating areas of higher and lower density. Okay? So, for purposes of multiple choice test questions, sound is a longitudinal wave. It is not a transverse wave. Now, this is really important because very often we will use a transverse wave to represent sound. And you got to remember that it's not a transverse wave. Okay, if you look here, you notice how the compressions correspond to the top of a wave. Remember what the top of a wave is called? It's called a crest. And the rarefactions, I'm going to change colors on you here, rarefactions correspond to the troughs. So although sound is not a transverse wave, we can use a transverse waveform to represent it. You and I, as physical objects, cannot occupy the same place or space at the same time. We can occupy the same space as long as one of us moves out of the way for the other, but we can't be there at the same time. Because waves are not physical, they actually can be at the same place at the same time. When they are, they add together. This is called interference. And they add together in the same sense that numbers add together. I'm going to put in this definition of reflection in between this discussion, or in between the panels of the discussion on interference, because later on we'll be talking about interference and reflections happening at the same time and what kind of wave they create. So if you go back to that drawing with the wave, okay, if you remember when you played with the slinkies, you were creating a wave by basically going back and forth, back and forth. Well, as you were doing that, the waves were traveling to your lab partner on this end. And if your lab partner just held onto the end of that slinky really tightly, the waves actually bounced off. So of course, as you're continuing to put more waves into the slinky this way, the reflections, the ones that are bouncing off your lab partner, are traveling in the opposite direction. Well, those two sets of waves wind up being at the same place at the same time, and they interfere with each other. So when the waves are synchronized, basically on the same side of the slinky, they use a rope here, it's the same idea, they're going to add together to give you something larger. This is called constructive interference, and of course construction means to build. So these two wave pulses, when they're at the same place at the same time, constructively interfere to give us a larger pulse. Now the question is, when these two pulses hit each other, do they bounce off and switch directions and go back to their original locations? Or do they actually continue on and pass through each other? Well, this is pretty easy to do as long as you make one of these a substantially different size than the other. You notice what happens here at the end, the small one is now on the left side of the drawing where it started off on the right. The only way that could happen is if these two bundles of energy actually passed through each other and continued on their merry way. The opposite of constructive interference is destructive interference. Now, this is not to imply that this guy and this guy are going to destroy each other, but at the point where they pass through each other or combine, think of this again as a positive value and a negative value because they're on opposite sides. So if this is a, I don't know, positive 5, negative 3, then when they add together, you're going to come up with something that looks like a positive 2, right? Minus 5, I'm sorry, a positive 5. These are just numbers I'm inventing. And a minus 3. Give us something that basically looks like a positive 2 without going into any gory details. Again, they pass through each other. You see the small wave on the bottom here continues traveling to the left just like it was in the first place. These two don't stop and interact. They split second basically pass through each other and continue on. So I mentioned that we're going to combine interference with reflections, those two definitions. When you're creating a wave on a slinky and your lab partner is hanging onto the end of it, the reflections interfere with the new waves that you're putting into the slinky. If you have the frequency of the vibration just right, you can create something called a standing wave. So if you created a single pulse, you would see that pulse basically travels along the slinky or the rope from, let's say, left to right. And you could see it moving left to right. In a standing wave, you don't see any left to right motion. It just looks like the wave is flopping in place. So this is what it looks like. At a given point in time, the slinky follows the solid black line. A split second later, it's going to flop over to the opposite side. So a crest becomes a trough, and the trough becomes a crest, and so on and so forth. And this thing vibrates back and forth. So it doesn't look like anything's traveling left to right or right to left. It just looks like the slinky is standing in place. That's why they call it a standing wave. In a standing wave, you have spots where you have maximum displacement from equilibrium. If you imagine that our equilibrium line would basically be running down the middle of this thing. If you had the slinky just sitting on the floor, not vibrating at all, that's where it would be. Do you remember what we call the maximum displacement from equilibrium? Either here or here? It's called an amplitude. So the areas of the amplitude, or the maximum displacements, are called antinodes. So antinode and amplitude both start with an A. That might be one way of memorizing that. The spots where you have destructive interference, so remember we're putting new waves in from the left and they're interfering with the reflected waves from the right in such a way that this pattern is created. The spot where no motion is happening is called a node. And I just look at the name node. NO is no. A node is someplace where no motion is happening. On a string like this, or a rope, or a slinky, you've always got a node at each end. And in this case, we have 1, 2, 3, 4 more nodes for a total of 6. And likewise, we have 1, 2, 3, 4, 5. I call them loops. 5 loops, or 5 antinodes. So in general, on a string, vibrating string or vibrating spring, you're always going to have one more node than antinode. See how you've got 6 nodes and 5 antinodes? That's because, in essence, you've got an extra node at the end here. You've got a node, antinode, node, antinode. So they come in pairs, and then you've got this oddball node at the end. Always one more node than antinode. This was my attempt at introducing the concept of the Doppler effect. And our most obvious experience with the Doppler effect is with sound. When you hear a car coming at you and then the car goes away from you, you hear a change in frequency or pitch. So I encourage you to Google some images of the Doppler effect. There's some pretty cool ones out there involving cars and trains, and basically it sounds like meow. It gets louder as it gets toward you. That's why this word gets bigger. And then as it recedes away from you, it gets quieter, so the letters got smaller. In addition to that, as it's coming toward you, there's a particular frequency or pitch or note, and when it passes you, that note drops down to a lower frequency, okay? This is called the Doppler effect. And it's really important that you remember that although we're using sound as an example because it's familiar, this effect applies to all waves. If you've ever been caught by a radar gun, know that that radar gun worked on the Doppler effect. You've probably heard of Doppler weather. Same thing. They're using waves that they're pointing at clouds, and when those waves reflect off the clouds, they can get information about the motion of what's going on in that cloud. So the Doppler effect happens because either the source of the waves or the receiver of the waves is moving relative to the other. And again, it applies to all kinds of waves, not just sound waves, but we're going to use sound waves because they're familiar. If the two objects, namely the source of the sound and the receiver of the sound, are coming closer together, then a higher frequency is experienced. If the two objects are moving apart, then a lower frequency is experienced. If you imagine a bug sitting in the water and just wiggling in place, let's say he wiggles once per second, and he creates these waves. These waves, just like dropping a pebble into a pond, move away from him in circles. And those circles are all nice and evenly spread out. If the bug is moving to the right, then basically he's chasing the waves that are moving out to the right. And you wind up getting circles that aren't centered on the bug. You notice how the waves here are closer together. The waves behind the bug are farther apart. In essence, he's chasing the waves that he's created in this direction, and he's running away from the waves that are behind him. Remember, the bug is moving to the right. And this happens because, if you remember from our previous discussion, we said that the speed of a wave is the same in a given medium. So the waves are moving away from the bug over here in all directions at the same speed. That's why the pattern that's created is a circle. Only a circle represents a bunch of points that are the same distance away from some center point. But over here, if he's moving in one direction and the waves continue traveling at that same constant speed, that means every time he jiggles, he creates a new wave that's actually closer to the wave that he made previously. So this gives us a shorter wavelength for the same speed. And likewise, we get a longer wavelength behind him. Well, if you remember, if v, the speed of the wave, is constant, then if the wavelength goes in one direction, what must happen to the frequency? How are wavelength and frequency related? Do you remember? You have a higher frequency on this side and a lower frequency on this side. So if you were, for example, standing over here, you would be witnessing a higher frequency coming at you as the bug is moving toward you. If, on the other hand, you were standing back here, then you would be experiencing a lower frequency as the bug moves away from you. Remember, the bug is moving to the right. A really interesting thing happens with sound when the creator of the sound is traveling at the same speed that the sound waves travel through the medium. In the case of airplanes, for example, this is called breaking the sound barrier. So here's our little plane. He's traveling to the right, and because he's matching the speed of sound, the waves in front of him never have the chance to move away from the airplane because he's keeping up with them. Behind him, the waves are farther spread out. Do you remember what a wave is? A wave is basically a bundle of energy. So this plane is piling up the front of these waves. All of this energy is piling up on itself. This is coming from the sound, basically, that the plane's making. All of this energy bunches up, and when it reaches the ground, because the sound is traveling through the air, when it reaches the ground, it creates, or we experience, something called a sonic boom. It's basically like thunder, except it's a single or maybe a double kind of boom or boom boom. And it arises from the fact that all of this energy is concentrated in one really tiny space. There's so much energy in that it can actually break windows in buildings. That's why planes basically are not allowed to travel that fast, because they would create all sorts of damage to cities, etc. And again, this would be known as breaking the sound barrier. As with the Doppler effect, highly recommend that you consider Googling images and other things about breaking the sound barrier. There's some cool stuff out there on the interwebs. Good luck.